Then starts up the video is too bad.
Hello and welcome everyone to today's seminar. I would like to introduce today's speaker, Professor Kashif.
Sir, एक मिनट
He is studying his PhD in computer science from the University of South Carolina. Assistant Professor at National University of Science and Technology. In China, he is working as an Associate Professor at the Department of Software Engineering in Beijing Institute of Information Technology. He is a senior member of IEEE, Associate Editor of IEEE Access, and Moderator of IEEE Archive. He is also a member of Pakistani Professional Forum in China and advises Pakistani students on academic issues. His research has been published in highly reputed research journals. For those who somehow missed this activity, a recorded version of this webinar will be available on YouTube. For those of you just joining us, welcome. We will have 15 minutes of question and answer session at the end of the webinar. So if you have any questions, just power them here. Professor Sharif, thank you for joining us today. We would love to hear from you.
प्रोफेसर शोएब की वीडियो पे वो
जो दूसरी वीडियो उनको बड़ा करना
that I have shared because I will be moving the slides and some of the PDF files. So if at any point there is some lag in the communication, or if you're not able to hear me or not able to see the slides, so just let me know and then we can fix it. Now, thanks once again. Assalamu alaikum everyone, once again. And today's topic is future internet model. More specifically, non-IP systems, software-defined systems, and blockchain influence. At the bottom of the first slide, you can see my email address. So if there are any further communications required or any knowledge that you want to gain or any interaction, I can be reached on this email address. So starting, these will be the three topics that we will be covering. The non-IP systems, which will be mostly focused on information-centric networks. We call them data-centric networks also, named data networking also, CCN also, so different name. Then we'll move on to software-defined networks, where we'll focus more on the controller analysis. And then finally, we'll see applications of blockchain networks. Now, over here, I want to emphasize that these are not small topics. These have been extensively researched in the past few years. Software-defined networks especially has been researched for a decade now. There are many conferences, many research articles, even books on all of these topics. So it is not possible to cover all of them in their entirety in 30 or 40 minutes. So I have made this presentation, it's quite lengthy, but some of that is just information. So you can just have that slide for information purpose. But my objective is to give you a fundamental orientation of what the topic is and what the research direction is and how to do research in these fields. So I will be consulting a number of papers while I am showing the slides also. So it is beneficial for students who are going towards their thesis either at undergrad level or master's level or even at the PhD level. To begin with, the current internet that we see, the way we are communicating, me, China, Dr. Mohsen, and another district of Beijing, and then you in a totally different country. if you analyze this communication, it is being enabled through internet. However, this internet that we experience today was developed many years ago, more than 3 decades ago. The initial design of this internet goes back to early 1980s. Many of us may not have been even born at that time. The objectives at that time were entirely different as to what we do today. The entire objective at that time was to have point-to-point conversation, the telephonic conversation, that is the beginning of data communication. So it's a point-to-point link where one entity talks to one specific other entity, fetch data or extract data or the network resources. It could be a file, it could be a picture, it could be any network resource from a well-known server, so you know the server's IP address or the server's name. And then we have a very well-defined and well-designed TCP/IP protocol stack for this whole internet communication, which relies on packet switching. Now this is the fundamental beginning of the modern day internet. Now I'm going to switch to paper that you should all read. It is the paper that was at the beginning of internet. This paper called The Design Philosophy of DARPA Internet Protocols. It was written in 1988. It actually talks how to design internet, and you can appreciate the people have no idea what internet would become, but many of their thinking or many of their concepts we see realized after 30, 35, 40 years of development. It's a very interesting paper and gives you an idea how to think for technologies of the future. Because if you do not think about technologies that will be available after 10 years, then your research is very limited and very less in scope. So understand the magnitude of thought process that goes into developing something that will be used for many years by people across the globe. So it's a total theoretical paper, but it gives you an idea how they were thinking about building internet. So they had their goals of a totally new technology. Similar to this paper, there is another paper called Protocol for Packet Network Interconnection. This paper came about 6 years before the other paper, the DARPA paper. This is actually the fundamental paper for TCP/IP. They did not call it TCP/IP at that time, but in 1974 they just wanted to build a protocol for intercommunication between networks. And if you read this paper, you appreciate how many problems they addressed that we experience still today, and we have better solutions based upon these things. Now, coming back to my slides, the objective is to understand that the internet has gotten old. The purpose it was built for has gotten old. Today's internet, although has evolved from many of the same principles discussed in 1974 to early 80s, however, its utilization has totally changed. And I'm talking from the perspective of a network engineer for the time being. We'll come to the software engineering part of it in a minute. But from a network engineering perspective, the initial objective was to communicate between machines, give them IP addresses or some identifier like a URL or a domain name through which we can fetch resources. In today's world, we don't really care about that. You want to find a video, you are interested in that video alone. You don't care where it is coming from. It is coming from a server in Pakistan. It is coming from a server in Europe, US, China. You don't really care as long as you have the content. Look at all the social networking sites or e-commerce sites. What you see in them is that they do not care where the data is coming from. Your data could be stored in multiple locations across the globe, but you want that tweet, you want that video to start streaming as soon as you click on the play button. So the fundamental change we see is we don't access a specific machine to get our data. We are interested in the content, not the data, not the source machine, but the data or the content itself. So where is the content versus what is the content? That is the question. We don't care if it's within the university premises or outside the university premises, within one server or within multiple servers. Irrespective of their locations, we are only interested in secure data that can be delivered even if we are mobile. And it should not fail. It should be available anywhere, anytime, with least amount of delay. So rather than where to go for the content in networking terms, we have moved towards what is the content or how can I get this particular content. So how do we modify the previous design goals of the internet where the objective was to reach a specific machine in order to get a web page, to how to find that particular data? So find an efficient alternative architecture to the internet, which is entirely non-IP based. It inherently supports the content-centric nature of the communication or the data-centric nature of the communication. Fast content retrieval is one major design goal, and other inbuilt features like security, mobility, they should all be present. This is the basic need for an information-centric networking architecture. The figure that is shown over here looks like a traditional network with routers R1, R2, R3, and so on. And then there are some content service providers like YouTube or other video services or audio services. And then there are requesters, the consumers, C1, C2. However, they are not communicating using IP. They are communicating using a name of the content. The content is secured by itself. The name is the only thing required to discover or find where the content will be. The content or the data will be forwarded based upon its name alone, not based upon IP. It will not be stored in one server. It could be in any of the routers. If you see the small databases along the routers, those are the cache stores or the caching points. It could be stored at any place. And the entire thing is connectionless. Fundamental TCP communication is connection oriented. Majority of our data transactions are connection oriented. The entire premise now is to be connectionless in a non-IP system. If you think about that from a networking perspective, you are effectively saying that we will not be using TCP/IP anymore. Remove TCP/IP and you cannot have a single data bit communication. However, ICN says that we will have non-IP communication based only upon the name of the content. So the consumer or the requester will request content based upon that name. That name will be forwarded among the routers till a router has that content by that name or a server has it, and then the content will be sent back. Entirely secure and on its own and supporting mobility. So when you start talking about content-based naming, you are eliminating IP addresses. Once you start to eliminate IP addresses, what you are saying is that we are not interested in identifying a machine. We will only give a unique name to every piece of content that is available in the internet. That means every video file, every audio file, every image, every web page will have a unique name. If you recall, we had IPv4 and then we had IPv6. The fundamental difference between IPv4 and v6 is the size of the address. Version 4 only had 32-bit addresses. However, version 6 has 128 bits for addressing. The need for increasing the address domain or address size is that we ran out of addresses from 32-bit domain. So if you imagine the amount of content we have, that is even huge as compared to the number of machines in the entire world. Giving them unique names to identify them is a huge challenge. Giving them those names can have many different types. Over here you can see hierarchical names, flat names. So many of them can be utilized. I'm not going into details about it, on how to give those names, but this is one of the research directions, how to give names to every piece of content that exists in the world. Then we also want it to be secure. Currently what we do is, you want to access some web page, you write the web page in your browser's address bar, google.com. What you don't see on the left side of google.com is www, and before that there is HTTP, Hypertext Transfer Protocol. And if you observe closely, sometimes it is HTTPS, which means secured. Before you open the web page, a secure session is created for you between your machine and the server that is going to provide you with that web page. This S is basically building a complete solution or a tunnel for you to transfer all of your data in a secure manner or over a secure channel. In named data networking or information-centric networking, you do not have any such channels or any such sockets. The packet itself, a single packet itself, should be secured independently. It should be self-authenticating, self-encrypting, containing the digest of the algorithm that is going to be used for that encryption and trust management. Now you can see we are slowly starting to move from pure network perspective to a bit of security and its implementation perspective, which is the objective of a software engineer. So most of these things ultimately will come down to the actual implementation, where the software engineer is specialized at. All right, another perspective or aspect of ICN or named-based communication would be the caching. Generally, when you communicate with a single server. You fetch all your data from there. You do not allow anybody to store that data. It's like you get a video from YouTube. YouTube does not allow anybody else to store and then provide you with that video. It's a copyright violation for them. However, the fundamental premise of named data networking is that it can be cached, it can be stored at any place, still providing the copyright to the owner of the data. How will that be implemented is an open research issue. How to cache, what to cache, and then how to provide still copyright protections, similar things. Once you have all of that, then how will the user find that content in the first place? You only know the name. What if you don't even know the name? What if we don't know anything? What we do is we Google it. So maybe there could be search engines, searching schemes, efficient searching database mechanics that can enable or build repositories for millions and trillions of digital resources spread across the globe. And then Even if you don't know the name, maybe you know some attributes like a video or a song by some specific singer. So if you know those keywords, you can find the name of the content and then request that name. So discovery and then retrieval of that model requires additional research directions. So some of them are NBR, LSR listed over here, lookup-based resolution, name-based routing. These are some of the suggestions, and there are others also. But this is again an open research question, how to discover the content and how to get that content delivered to you across the internet from the closest location to you. One of the implementations of this entire new internet is NDN, named data networking. This is an open source project. You can just Google it and you will find the complete source code for all of the implementations. A similar project, which is a bit proprietary by Cisco, is called CCN or CCNX. That is content networking. Same thing, very identical in design, but NDN is more open source. So the blue lines or the blue keywords you see over here are the key. Use content names instead of source or destination IP addresses. No need of the TCP/IP stack. Unique content names for the communications. NDN keeps track of all the states of the packets and can be tuned to very application specific scenarios. Now, this is the big picture, which I've already talked about, that it should be self-contained. The packet should contain the data as well as its encryption digests, verification mechanisms, signatures, everything. So that is already discussed. This is the picture that I want to show on the right side. There are two hourglass figures. The left one is the traditional TCP/IP stack that has evolved over the last 2-3 decades. At the top, you have your applications like email applications, browsers, other desktop applications that you use, or smartphone applications that you use, running over protocols like HTTP or real-time protocol or other things that enable the interaction between the user and the device. Below it is the TCP or UDP protocol that is going to allow end-to-end communication. And then the glue that binds internet together is the IP, internet protocol. That is where everybody is on the same page. If your machine understands IP, it can be part of the global internet. Regardless of the technologies below, either you are using Ethernet 802.11 version, 802.3 version, you are using a wireless system or a copper wire system or an optical cable, lower technologies do not matter if you understand IP. The hourglass figure on the right side does not have IP as the glue. IP is lower in the stack, which makes it irrelevant. Not entirely irrelevant, but not as relevant as it is in today's internet. IP will just be one of the technologies that can be used for node-to-node communication. What you will have is the name of the data. On top of that, there will be a security layer, and below that, below it will be a strategy layer. Strategy will be how to find and forward and deliver the data. The security layer above it would make the data itself secure, not through channels, but the packet itself is secure. So there is no dedicated transport layer for end-to-end communication, nor there is any IP-based identification mechanism. So see, it's a complete game change. You are not going to be using the existing networks as they are. Now, the rest of the slides about the NDN talk about the naming scheme, that there could be names that are very similar to the URIs or URLs that we have today, and that could give you a very good idea how unique names can be generated. However, it is still an open question. The longer the name, the more data it will contain, hence becomes a control overhead challenge. Similarly, you can have very specific communication models designed for the new systems. Currently, what we have, you want to get a web page, you generate a an HTTP GET message. In response, you get an HTTP reply. Below it, it's encapsulated into transport layer packets, then IP packets, then data link layer frames, and then the physical layer transmission. And then you have multiple TCP IP packet communication, bidirectional. The communication model that NDN says consists of only two packets, an interest packet on the top right, and then a data packet on the bottom. You want some data, you have a name for it, you put it in the content name, provide some preferences for it, how quickly you want it, what it should be the data rate, any filtering mechanism, and then the nouns, which is a security mechanism in there. It is unique for it. So you just send that interest to everybody around you, and whoever has that content with that particular name creates the data packet and sends you that data back. It is signed, it has signatures in it, it has the algorithms that will be required to verify it within it, along with the data. And that is it. No connection establishment, no connection tear down, nothing of the sorts that we see in TCP IP model. So a very, very simplified communication mechanism where the objective is to find the content, find that image, find that video, find that audio file. Nothing else should be going over the network. This would require a complete architectural change at the access level, at the core network level, in the routers, in the switches, everything. Your current routing tables or the routing protocols will become obsolete. You require new routing protocols, new forwarding mechanisms. This is just a small picture of how the new forwarding tables will look like. They will have content store tables, pending interest tables, forwarding information bases. I'm not going to go into detail how the process works, but this is just the beginning idea that there should be these many tables. Some research papers suggest there should be more tables. However, again, an open research question that the routing table is not going to contain an IP address. It is going to contain a name, and it would be very simplified. I don't get into details of how a routing table behaves or how to look up into a routing table, but the challenge is routing tables are very, very complex. They can be simplified. They have many columns. We want as less columns as there can be. From a database perspective, you can always appreciate whenever you normalize a database, you want to create tables that are smaller in size, in the number of columns, I mean. That is why you normalize and separate them. You don't want redundancy in columns. So same concept over here. The more the columns, the more complex it would be. So we want less columns along with the name. So how to do that? How to achieve that? Then how the forwarding will work. This is a very abstract idea of how forwarding works. You send an interest to the top right box. You send an interest packet. It is stored at the router. There is a pending interest table where you see if we have the data. If we don't have the data, we can forward it to the next hop router where we think the data might be. And if it is available, it will be delivered back downstream. Otherwise, you will keep on forwarding until you are unable to find the data and drop it. But this is a very, very crude and very, very basic way of forwarding. You don't want to flood the network. You don't want to send the request to every possible person in the internet. So how to control that becomes a research challenge. So ultimately, the routing that has evolved for many years in many forms will come down to very simplistic rules or the strategies or policies that will govern how data as well as requests are forwarded. If you look at current routing protocols, the RIP, RIP, many versions of it, OSPF, BGP, they have been developed over many iterations. There are RFCs and standards with them. So it would be very difficult to replace them immediately. However, they have become very bulky and very complicated. They were designed for IP-based systems where IP is starting to matter less as compared to the content. So at some point, they would have to be replaced by something that is better. The in-network caching, as I said earlier, one of the biggest challenges, what to store, where to store. We are not interested in dedicated servers or dedicated data centers anymore. We want the content to be fetched from the closest person to you. Imagine a scenario where you are sitting in this room, maybe about 40, 45, 60, maybe 70 people. Now, if one of you watches a video on their mobile phone, what effectively they are doing is getting the video buffered on their device. Now, one other student also wants to watch that video, and they go to the YouTube and they enter the same keywords, find the same video and start to stream. What you are doing is two people who may be sitting next to each other fetching data from a server that is in a totally different continent. Two streams for identical data coming from the same server many thousands of miles away. Why can you not stream the same video from the person who just downloaded it or buffered it? That would save so much resources. It will be so much quick and will reduce the burden on overall network. That is where the caching is. If everybody can store the content that they have recently accessed, anybody closer to them can immediately get access to it without any delay. That is the objective or premise of caching. But should it be allowed? How much of it would be allowed? Will people be able to share without any security concerns? That becomes a research challenge. So there are many strategies for cache placement, cache retrieval. So not going into detail, but there is a lot of work on that. You can find it in many journal papers. Then we have the same issue with the forwarding strategies. You forward the data to somebody else over multiple hops. How to discover those hops, how to utilize the multipath problems. Traditional routing protocols were not multipath. Later on, they become multipath routing protocols. So if you want to have multipath communication built into the new internet, how to do that? How to use multiple interfaces. All of your modern day devices have multiple interface. Pick up any smartphone. It has a Bluetooth interface. It has a Wi-Fi interface. If it has NFC, many of the Android phones have NFC built into them these days. So at least 3 interfaces. Pick up your laptop, it will have wired interface in addition to the Wi-Fi and the Bluetooth in it. So why can you not use all of those interfaces for internet communication? You should be able to do that. It would become more simpler if the communication is content-based rather than IP-based, because Bluetooth interface does not have an IP. NFC does not have an IP. So what you do, you remove the IP from the equation. On top of that, all of this should be secure. So a huge research direction in the form of security is open for named data networks or content-centric networks. Now, I'm going to go a little bit faster because this is some of the information that I've already said. The privacy, mobility, all of those have to be built into this concept of data-based communication rather than IP-based communication. Now, here is something interesting, the functional differences between current internet and the NDN. The whole addressing structure in NDN is named based rather than IP based. So the previous routing was based upon IP prefixes. Now it should be based upon name prefixes. Previously we had the routing protocols. Now we will have name and nonces for the routing. Previously, all the forwarding at the IP layer or internet is stateless. You send a packet into the internet, there is no guarantee that it will be delivered. The higher layers make that guarantee for retransmissions. However, in NDN, the state is completely forwarding, which is going to put burden on the intermediate routers, however, makes it more easier and safer. Same thing, forwarding strategies previously were stateless, now we want them to be stateful. Consistent routing tables, you build them, they remain there until the topology changes. Now in NDN, we don't have topological change issues. We just want the content from wherever it is possible. So we want probe messages to find the content rather than the topological information and things like that. Data manipulation and data transfer comparisons in this particular slide, where you see that current internet error correction, error detection is the responsibility of specific layers. NDN will leave some of those responsibilities to those layers. However, it will shift some of the security measures like encryption and then session management to other layers, as we saw in the slide where we had the R glasses. Now, I'm going to summarize the open research challenges over here specifically. So if you're looking for a research topic, these are some of the research questions that you can just pick up from the new internet model. So you can talk about flat names versus hierarchical names. And even if you try to build a specific type of naming structure, then there are many different issues in there, starting from the size of the name to how elaborate it is, how well defined the name itself is, how scalable it becomes, how quickly searchable it becomes. So many topics within the name researches, name base also. Then the routing, how to find them, how to map them, how to discover the content, to how to forward the content. Should everybody have a global view of the internet? Should it be limited? Scalability issues, dynamic environments, wireless devices, all of them then start to build different research questions within the overall system. Routing and forwarding fundamentally are two different things. Routing mostly discovers how to find the paths, and then forwarding is how to pick the best path from them. So even in NDN, it will remain the same. How to discover the content and the paths to that content versus how many paths can you take simultaneously to retrieve the content or same content from multiple sources. So that becomes a totally different research question. Then the problems that exist in internet, like internet breakages, congestion, they will become, they will still be there, but from a different angle, slightly different angle. And how to tackle them are again research questions: load balancing, congestion control, link failure, detection of malicious attacks, denial of service attacks. They become totally, you can see them in a totally new light from the perspective of name networking. Phishing, I've already talked. A major challenge, how to optimize it, what to store, when to store, where to store. These are the three questions fundamentally that need to be answered. Mobility, we all want to be mobile. Nobody wants to have a desktop anymore. We all have laptops. We have mobile phones that we get content on. We want to keep on moving and should be able to get access to the same content. We developed cloud computing for this. However, if you remove IPs and you allow content to be cached anywhere, your mobility becomes a bit different. Previously, you had a specific channel or a specific link to a server and you were getting the content. However, now you're getting content from random points. Hence, if you change your access point or change your cellular tower, the data that is on its way may get lost. So how to address that is a research challenge in itself. Security and privacy, it's a huge domain. How to secure anything is always going to be a problem. So not just the encryption, we're not talking only about the encryption algorithm, the signatures, how are you going to authenticate? Traditionally, we have a CA, a certificate authority, or a central server which manages all the keys. It provides you the key to encrypt anything if you just open a browser. However, If there is no central authority, every data packet is independent, how or who will authenticate? How do you design a mechanism that is self-authenticating? It kind of like sounds weird that I can authenticate myself. How do I get the authority to authenticate myself? So if everybody has the authority to authenticate themselves, how do you distinguish between a malicious packet and a legal packet? So however, there are algorithms which can only be generating self-authenticating signatures. So that is a still open research question. Interoperability, you cannot replace a complete internet architecture with a totally new one without having interoperability challenges. Okay, so I see that the video link with the students is kind of buffering. So I'm not sure my voice is reaching everybody over there or not.
Please let me check.
Okay, so the video is back. So I hope that if anything was interrupted, let me know in the end and I'll try to repeat that part.
There was an unstable internet connection, but we have reached your
Okay. Okay. So if there is anything missed out, you want me to repeat something, you can ask me in the end. So I'll go over those slides again. In conclusion, for this part of the discussion, ICN and NDN, they are still very, very new. There are test beds for evaluation. There are open source resources for them, but the objective is that this is the right time to contribute something to it. Maybe 10 years from now, ICN or NDN will be part of the global internet, at least to a certain extent. It is already used in many of the places, most specifically data centers. Facebook data centers internally are entirely name-based. They are not IP-based. You request an image on Facebook, you are communicating with the NDN data centers on IP, but within the Facebook's data centers, it's entirely name-based. The name of that image is what they find and give it to you. And it could be coming from any of their data centers across the globe. So it is already being used. We need to have short-term designs and long-term designs to be part of the upcoming system. We have to be open-minded about ICN and NDN and see if we can contribute something now that people will still be talking about 10 years or 20 years later on. Okay, so that is where the one of the internet models is. Now, as I said in the beginning, that most of this is networking based. However, implementation of all of this will be software based. You cannot have any of these algorithms designed without software implementation. You will require new types of databases. You will require new types of searching mechanisms, which are all the domain of software engineers. You will require new types of browsers, applications to exploit the content-based communication. So I only defined how the communication will happen. There are still many questions on how that communication will actually happen. But to really utilize it, we need the applications. Internet would have never grown to the size it is today if there were no applications to utilize it, if there were no distributed databases to support it. Communication is the underlying glue. Utilizing it is your applications. Now, what if we put applications into the networks? What if the network can be configured, designed, controlled by an application, which is your software-defined network? You are not binding it to some physical wires and a specific topology. You are saying whatever topology physically is, we can reconfigure it in a software-defined system. The interface of the software can give the user an option to create a topology of its own, regardless of what the topology, physical topology at the backend is. Now, the fundamental premise of an SDN is that we do not use the topology of the system and then be fixed to that topology. If you look at a traditional network, this figure has two parts, the left part and the right part. The left one is a traditional networking architecture, where you have intermediate nodes, so which are connecting different networks, your routers or your switches. Any router or an intelligent switch, not a general dumb switch. I'm talking about an intelligent switch or a router. Has two parts, a data plane where the forwarding fabric is there, the electronics of it that connects one interface physically to the outgoing interface. And then there is an operating system running on it we call the control plane, which is basically a software. It's an operating system. Any router has an operating system running on it, which makes all the decisions, where the packet will go, where the routing table is going to be, how it is going to be processed. All the packet processing is software-based. So that is the control plane. Software-defined network says, the figure on the right side, leave the physical part on one side and then take the control plane and centralize it, making a network operating system, a software-based system where you can reconfigure the switches or routers. Routers and switches become the same thing effectively. You can just reconfigure them from a single point. And that would be the control plane. And it's not a complete plane, it's a single controller. Now, this gives you fundamentally a simpler device. It's just a hardware device. It reduces its complexity. You can have programming abstractions all the way from the physical forwarding to any kind of policy, either it be security or access control. Network management becomes easy, then it becomes a GUI piece of software where you can easily create virtual machines or virtual networks out of physical networks. It becomes language independent. You don't have to worry if it's written in Java or C++. Promotes innovation and then gives you total control over your network. You don't really need a person to physically change the wires or install new devices. You just have a data center, and out of it, you can create any type of network you want. Effectively, it will start to look something like this. The data plane at the bottom is just a collection and connection of switches or routers, and then the networks are connected to them. Then there is this huge control plane where you have SDN controllers, dedicated servers running network operating systems that are going to configure the data plane devices using southbound interfaces. What are southbound interfaces? They are only APIs. APIs that take instructions from the controller to the switch and configure it. OpenFlow is a very common southbound interface API. A set of instructions for configuring the switches and routers. Above the control plane is your management plane where your applications will run. They can be running directly on the controller or remotely, virtually anywhere connected through REST API or any HTTP request to the controller. So the focus then becomes on the SDN controller, which is a piece of software that is going to dictate how the network is going to behave. So let's talk about the controller itself. It's the brain of the whole network. You can configure through it anything that you want. It relies on APIs, either southbound or northbound, to communicate with the applications above and the devices below. Control from a single point all your network traffic, packet flows, policies, automation, everything. So it's basically a network operating system that you can very easily utilize to program the whole network. Programming of the networks is not new at all. Programmable radio networks go back to early 2000s. So it has been there for a very long time, and many organizations have been using it until it became more popular, and now almost every large organization uses it. This is another view, but the emphasis in this figure is the central part where you see the controllers. There are many controllers: POX, NOx, Floodlight, Cryo, ODL, Open Daylight, ONOS. There are many different types of controllers. So what our focus today will be on the controller itself. There have been so much development, but there is still so much left out in the form of controllers. So one of my students got a task. I gave him a task that why don't you first compare these controllers? How can you compare one piece of software to another piece of software? Fundamentally, the software is going to control a network, so that software's performance dictates the performance of the network. If it is good, the performance of the network can be expected to be good. So how do you evaluate a piece of software? I'm sure that there are many software engineering techniques in order to evaluate the internal working of a piece of a software. But when you evaluate a piece of software from its applications perspective, you have to be mindful of many things. So before we go into detail, let me just quickly show how a controller works. Basically, the objective is to forward or enable forwarding of data. So controller is connected to many of the open flow switches, the OF switch, that is an open flow enabled switch. That switch is connected to different computers, laptops, access networks, mobile devices, etc. So whenever you send a data packet from your laptop to your switch, and if that switch is part of a software-defined network, it will ask the controller how to forward it. It will not make a decision on its own, so it is just going to focus on the forwarding part. So it asks the switch for the details on how to process and forward it. In response, the controller will tell how to forward it and then will build a path for it across all the switches and routers to the final destination. So everything is upon the controller to do. It has to build the path, tell the switches all the paths and the parameters, and then you can enforce all the policies and access control using the controller. So if you want to compare the controllers, first you find out, okay, what are the qualitative properties of different controllers? Just like you look at two operating systems. Let's say you look at two operating systems, Windows and Linux, and let's add Mac OS to it also. So if you want to compare them, what do? You can evaluate it from two perspectives. One is the qualitative performance, and then the other one is quantitative performance. So in qualitative performance, you can think of things like this. What is the programming language used? Every programming language has its own good points or bad points. C, C++, very good in low-level programming. The operations, mathematical operations done by C are still unmatched by many of the modern day programming languages. So you need to find which programming language is going to be better for a specific type of applications. So some of the controllers are written in C and C++, very large programs. Some of them are very efficient. However, there are many other programming languages also like Java. So you can capitalize on their benefits also. We can have controllers that are multi-threaded, capitalize on memory management. So some of the modern day protocols like, controllers like ONOS and Open Daylight, they are written in Java, gives you platform independency also. So some of the controllers have good points in that manner, but maybe their operations are not as efficient as C, C++ controllers. And then just like any other programming language, you have Python and scripting languages. Controllers also have been implemented in those languages. That does not mean that it makes a better application or better program. It's just a language. The fundamental reason to put these three slides over here for a software engineering student is to make them understand that the application should not be dependent upon the language. Language is just a tool. You need to find which language would be best for this application or this implementation, and then use it. Although Python-based controllers are very faster in compilation and debugging and simpler, however, they are not as effective in managing large networks as compared to some of the Java or C++ implementations. So always remember this. Language is just a tool. You can never be an expert of Java or C or C++. That is only a myth. Never run behind a specific language. It's just a tool. Think of an artist, a painter. Sometimes that painter will use watercolors, sometimes sketch pencils, sometimes charcoal, sometimes some other tools. So all these are tools. None of them makes him a better artist. What makes him a better artist is the skill and imagination to draw. Same thing goes to any application, either it be a controller or any other software application. You should not be an expert of Java or C, C++. You should know programming, building logic, the constructs of logic. After that, language is just a tool. You can pick up a book, learn it in 24 hours or 7 days. Now, this is what you should be providing inside a controller. Many different modules. You see, storage manager, flow manager, decision making, topology manager, link discovery, all of them require different types of data structures. A topology manager is fundamentally a graph. How do you store a graph? The easiest way is to maybe use a matrix, maybe a multi-dimensional array, but it could be too heavy. So maybe you design your own data structure for it. Which language would be most efficient in doing matrix manipulations or fundamental graphs? Could be multi-directional heap structure or a tree or even a complex linked list. So all that boils down to efficient implementations of these things. All of this looks like networking. Fundamentally, it is enabling networking, but all of this is software engineering. If you do not have a good algorithm implemented, communication would lag. You look at the top part, the SDN application plane. All of them are applications communicating with the controller. The northbound interface between the SDN applications are all REST and HTTP APIs. So there is no fine line or no distinction where networking ends and where software engineering starts. You have to be knowledgeable about the relevant fields that you are defining or designing an application for. So you look at all the architectures of different controllers. Most of them have things that are API-based systems, file-based systems, socket-based systems, or databases running in the backgrounds, web services, UIs. So all of that is software engineering. Part of it is networking, enabling networking, but again, it's all implementation. Look at the components given by the Open Daylight, one of the most commonly used and largest controller available. The top part is all applications, the orchestration applications, control applications, third-party apps, and even the central part above the blue line. Blue line is some of the data storage. So again, databases in there. But even at that part, authentication, authorization, accounting, container orchestration, service function chaining, all of them is software engineering. It does not matter if the name takes network virtualization. If you're going to virtualize a network, fundamentally you are doing software engineering of networking. So always try to get as much knowledge of other domains as possible so that you can develop applications for them. If you look at the left side, the platform services, you see JSON, RPC extension. Is it really networking? Not entirely. All of JSON is software engineers' bread and butter. So if you are expert in that, you can contribute to controller design, controller development. Look at the ONOS. This is an open source network operating system. All of these are software-based components, replaceable software-based components inside a controller. How to do qualitative comparison? I said in the beginning. This is a small table of qualitative comparison. Now here is what I said in the beginning, that I've tried to put in elements where you can do a little bit of research in there also. How to compare different controllers. First you categorize, make the left column. What are the categories which we can use to compare different things? This is a very small table. The actual table that we had in the paper was quite large. Let me go to it. Okay. I'm not sure how visible it is, on that screen. I'm trying to magnify it, but this is a set of 32 controllers, and all these columns are different variables for their comparison, starting from is documentation available from them, or multi-threading available, or licensing, or GUIs available for them, or what is the architecture, centralized or distributed or hybrid, what is the language used. So you can see how to do the qualitative analysis at a large scale. So we collect all this information and then analyze it. This is the beginning of research. You should be able to find what to compare in two pieces of software. What are the points where they can be compared? So all this blue line at the top, that is the points which can be compared. Okay. So once you have done the qualitative part, then you can move on to quantitative comparisons. So this is a small part from the same table. This is another part from a different comparison perspective of 4 different protocols, from their traffic engineering perspective, their load balancing perspective, the network monitoring perspective, etc. Some of the controllers are not only for one type of technology. Some are for wide area networks, some are for IP networks, some are for optical networks. So the control then becomes more and more complex. It not only is bound by IP, it is bound by many other things, flow labels. And in the end, we'll talk about same named data networking, how to design controllers for named data networks. So coming back, we wanted to evaluate or compare controllers, which are pieces of software. And we said, okay, there can be qualitative comparison. And then we can see how they perform also, because the way they are implemented will have a huge impact on their performance. A very small example is, and you can try doing that by yourself, take one data structure and compare it to another data structure. You can store data in an array. You can also store the same data in a linked list. Let's say one integer, you want to store a single integer in an array and the same integer in a linked list. You can always see which data structure is going to take more memory, which would be easier to search, which would be easier to sort. Same thing happens when you implement a system. A bad software engineering principle will give you a bad effect in the final application. So I'm not going to go into detail about each and every network element, but we looked at different ways we could evaluate, like what would be the throughput of the overall network if we use one piece of software. Ultimately, from a networking perspective, we want high throughput. And if the software is bad, it's going to give you less throughput, then I don't want to use that kind of software. So these are only a few metrics that we compared. In reality, we compared several of them. It was a huge table. Let me go from the paper and show you that table. This table. Okay, so on the left side is the grouping of the variables that we wanted to compare for pieces of software, because that is where networking perspectives comes in. Throughput, latency, flow related measures, how topology is stored, how it is modified, how threading is done, how threading impacts the efficiency of the overall system, and some other parameters. So once we decided upon that, then we came back and did this. We said, okay, can we compare any controller to every other controller? Not necessarily. Can you compare every operating system to every other operating system? Maybe, but not necessarily. You can compare an operating system that is designed to run for a server to an operating system that is designed for an Arduino device. So they are miles apart. So you have to categorize and classify. You do this in quality assurance of software engineering also. You find points where you can actually measure quality. You cannot compare oranges to apples. Same thing we did with the controllers also. They are different. So we categorize them, how they can be compared in what terms. And then the last question that we had to answer was, what tool are we going to use to compare? We want to actually compare the performance in terms of networking output. So there are many tools. We picked three, the highlighted ones. But again, as a software engineer, you are aware there are different quality assurance or testing, software quality testing techniques. You do black box testing, you do white box testing. So there are different techniques, and all of them have their benefits. All of them give you different types of outputs. So we also chose what the tools were, and then some details about the tools. Let's not go into details. And then we set up a topology similar for all the controllers, put up the controller, and then we ran the controller for some amount of time and wanted to see, will they perform similar or comparable to each other? So we implemented 9 controllers. Actually, we initially found 32 controllers, close to 40, but we found 32 which had some information available or some source code available, partially, at least enough to do a qualitative evaluation. Out of those 32, we only found 9 had actual implementations available. And out of those 9, I'm only showing you one graph over here. The latency. Latency is the delay, how much time it takes for communication. Over here, we are saying, okay, how much time it takes to do the flow installation when you contact the controller and when the actual data starts to flow. So that is latency in terms of flow installation time. So on the left side, you see the time in milliseconds, and then you have the number of switches, which is the scalability of the network at the bottom. And the different lines are different controllers. And you can immediately see, let's look at figure A alone. You can immediately see that some controllers have less latency, which is good, and some have very high. Overall trend is that larger the topology, latency will increase. That we already know. But why do they have different latencies? The network is the same. The network link capacities are the same. The number of devices are the same for any given instance. Everything is same. The only difference is the implementation of the controller. The ones that are taking more time have implementation issues. They use data structures that are not optimized to store topology or to store routing tables or to search engine. Some of them who are better, then they provide enough components in them for being a better controller itself. They do not have enough APIs available. And the 3 different graphs actually are from the 3 different evaluation tools that we used. So you use one technique and find out, figure A, that the maximum time was 350 milliseconds. Same controller, same topology, but you change the tool to evaluate and you get a result. Look at figure C. It goes up to 1,000 milliseconds. Same, everything is same. The controller is same, the topology is same, everything is same. So what does that tell us? Bad implementations and bad evaluation techniques, tools that are not good at evaluating things. One should be mindful as a software engineer. Does not matter which application you are building. I'm a totally networking person. I know nothing of white box testing or black box testing internally. I know what they do, but if you want me to implement a system that does that, I can do that. I'm a networking guy. But for me, a controller that has been implemented poorly and gives bad performance in same environments is a software engineering problem. So at the end of the day, when you go into the market, you will not be developing only small applications. You will be developing applications that may be used over the internet. You may be developing applications for databases, backend developer, front-end developers, UI developers, full stack developers. What is a full stack developer, by the way? Who can do everything, starting from the user interface all the way to the backend. That is a full stack developer. So you need to know the other accompanying domains and then how to optimize your software implementations for them. Now I come back to my interest. How can I integrate a non-IP system into a software-based system, a software-based network at the controller level? I want to remove all the complexity of traditional routing, IP-based system, and put it into a single centralized controlling software that will be based upon a name of the content. And then it should be able to provide services to vehicular networks, to 5G systems. It should incorporate intelligent machines in there, also automated machines, also machine learning components, also everything. That is the big challenge. That is the future of the internet. SDN is already being used. ICN testbeds are already there. Data centers already utilize NDN technology. So we need to merge them so that the next internet can be more fruitful. Centralized architecture, distributed architectures, complete state or complete slate architectures, overlying under architectures, underlay architectures. These are some of the directions that can be taken while going over SDN, ICN based controllers. And this is just a fundamental figure my student view to show how a centralized system or a centralized controller versus a distributed controller would look like. So it gives you an idea that there will be a lot of communication among them, or single controller, but then they have totally different ways of implementations and the APIs that would require that or that would enable that communication. I'm going to skip on this because this is already what I have said. I want to get to this part. Now, Google had a big problem many years ago. Their data centers were getting too big, difficult to handle. Links break and then you have to manage them again. So what they did was they built up their own solution. They built their own software-defined networks proprietary for them. If you ever get a chance, read this paper, B4, Experience with a Globally Deployed Software-Defined Wide Area Network. It talks about how Google's data centers are interconnected across the globe. I think I have the paper somewhere. Yeah. Now, if you can see this figure, these are some of the data centers of Google across the globe. They are all interconnected using software-defined controllers. Controllers that are super efficient, super fast, that if you fetch a single search, if you do a single search, some part of that results would be coming from one continent and some of them would be coming from another database on another continent. And usually Google shows you how much time it spent searching for those results. So this is the speed of that controller. After that, it is the optical networks below. So we assume that they are super fast. However, the controller that is going to integrate all this is going to be super fast at the implementation level to enable it. So this is a very interesting paper, although it's a networking kind of paper, but if you read it, you will find out how they actually designed the overall system. If you look at this figure number 2, this is all software-based system architecture. So if you ever find time, read this paper. Actually, it's not new. It was in 2013 or 14, sometime around that. 2013. Okay, so it's not a very recent paper, and most probably they did the development way before that. So all of these things are already being used, but in isolation. The future would be the same systems becoming global. Current internet was isolated also. Few universities in the US were just exchanging information, small web pages. Now it is global. So this would become global someday. Maybe something that you develop would be part of it. Finally, I want to quickly talk about blockchain networks because that is also hot and everybody wants to talk about blockchain networks and implement blockchain and everything. I'm not going to go into too much detail of it. I'm just going to show you one paper. Actually, it's an implementation of blockchain for e-healthcare systems. The title is Easier Said Than Done. We published this paper last year when it came out. One of my PhD students who has graduated now in Surrey. He was the first author on the paper. So I'm going to switch to this paper, and I would like that you see now how a paper is written. This is a completely theoretical paper. If you can see this, I have highlighted this, and I will share the paper, the highlighted paper, and you can look at it. But every sentence is specifically designed to address a specific point. The objective of this paper is to establish that this hype of blockchain should be very carefully analyzed. If you want to implement it in an e-healthcare environment, first of all, whenever you hear about blockchain, you immediately think about cryptocurrencies. And our first heading was, don't think cryptocurrency. Ethereum, Bitcoin, they are not what we want blockchain to be about. Not everything is about cryptocurrency. A common mistake that we find in today's blockchain implementations is tokens, and everybody wants to integrate those tokens into any application you develop. No, that is not going to happen. So do not think cryptocurrency. Think about business blockchains. And this is what a business blockchain looks like. It has nothing related to cryptocurrency. This is a generic architecture for Hyperledger. Hyperledger is an IBM solution for business blockchain. It has many variants. If you find time, have a look at the IBM solutions for blockchains, and they are totally business related. And business is not like financial business. It could be any process that can be automated. For example, access control, that could be implemented using a blockchain. And when you talk about an application area, for example, healthcare, you have patient records. Those are assets. You can implement blockchain to secure them. However, you need to be aware what the pitfalls are. So if you have some knowledge of blockchain, then it would be easier to understand. Otherwise, you should do some reading on blockchain, and then you'll be able to understand the complexity. This is a figure that we made to show how the traditional system, the gray circle on the right side, will go into a blockchain-based system, which is coming from the left side, the brownish tan circle, into a combined, coexisting traditional and blockchain-based system. This is not what Bitcoin or Ethereum looks like. This is a totally different thing. So the integration of traditional systems with blockchain systems is one of the biggest challenge. If you try to read research on blockchain, most of those papers, 99% of the papers just ignore that there is a traditional system. They just start that you have a blockchain network, which is impractical. You want blockchain to be part of the next generation network or internet, you need to be aware how it will be integrated with the traditional system. What components can be directly merged, what components cannot be merged. One of the next biggest challenge is this figure. Now, it looks like circles, but the top left circle is a complete standalone, pure, single unified blockchain. And what we are saying is, assume that there are 3 hospitals. All of them want to be part of a blockchain system that is implemented at national level. We don't have a national healthcare system in Pakistan. Many of the developed countries have. If we want to develop such a national healthcare system, we need all the hospitals to be connected to a single repository. You go to one hospital, your medical records should be available there. You go to another doctor, your medical records should automatically become available over there. You should not have to take your medical history as a file to different hospitals, and every time you see a new doctor, you have to explain them again what has been happening to me, especially with elder patients. Becomes a huge problem. Fundamental thing in a modern healthcare system is the availability of records. And you can automate that by blockchain. All you have to ensure that is all the hospitals are connected to the same blockchain. Or the right side figure, the top red circle, even if they have separate blockchains to store and secure systems, they should interact with each other. So the paper talks about the solutions, how it can be done. But these are the challenges that will arise once the implementation of these systems start. As a software engineering student, implementing a blockchain solution would be the thing to do. Any application, modern application that you develop would somehow try to integrate security, and blockchain may become part of it. So how do you do that? What should you be aware of? So this is a totally theoretical paper from that perspective. Uh, I'll again show you the title of it. It's published in IEEE Computer. So find it, read it from a totally software engineering perspective. It gives the fundamental details of what a blockchain fundamentally is, and then you can see what pitfalls are there for you to look at. So I'm going to stop here. I'm not going to go into detail of each and every element because then it will take a lot of time. If you are interested, and Dr. Mohsen is here, if there is a need, or if students or teachers are interested in talking more about blockchain in depth, we can have a totally separate session for it. So that is all that I wanted to talk about. It has become quite lengthy. So I'll stop over here and I'll take any questions that you have now.
Thank you very much, Dr. Saab. It was really interesting talk and we enjoyed it. Questions from students especially. If anyone has a question, please come forward and ask.
Thank you, Dr. for telling us where you're going to. If any question, raise your hand so that we can solve it.
मेरा क्वेश्चन है कि is there any distributed platform software defined network क्योंकि हम इसलिए नेटवर्क चार इसके चार एक P2P peer to peer नेटवर्क बनाया हमने सेंट्रलाइज से जुड़ा है that SDN may be highly controlled centralized, there will still be problem. So is there any design distributed control plan or is there any mechanical plan? Thank you.
मुझे पूरी तरह आवाज नहीं आई, बीच में काफी उसकी डिस्टॉर्शन थी. डिस्ट्रीब्यूटेड प्लेटफॉर्म आप जानना चाह रहे हैं. सो इस उसमें जरा दोबारा एक्सप्लेन करें या टेक्स्ट में मुझे जो है ना इसी में वो टाइप कर दें, वो बीच में डिस्टॉर्शन की वजह से मुझे पूरी क्वेश्चन समझ नहीं आई.
Is there any distributed control plan? Yes.
सॉरी डॉक्टर साहब, मुझे लगता है कि डिस्टॉर्शन बहुत ज़्यादा है. हम इनसे रिटन क्वेश्चन लेंगे और आप तक पहुंचाएंगे.
हाँ जी, बिल्कुल. आप उसकी पूरी एक लिस्ट बना दें, मैं रिकॉर्ड कर दूंगा, वॉइस रिकॉर्ड कर दूंगा या टेक्स्ट में.
जैसे अभी एक क्वेश्चन है, इज देयर एनी डिस्ट्रीब्यूटेड कंट्रोल पैनल इन एसडीएन और हायरार्की?
Distributed, there are different controllers which are distributed in nature by default. उनमें आपको जो ओपन डेलाइट है उसका भी डिस्ट्रीब्यूटेड प्लेटफॉर्म मिल जाता है. इसी तरह 2-3 और कंट्रोलर्स हैं जो कि डिस्ट्रीब्यूटेड इन नेचर हैं. और जो हमारा जो आर्टिकल है वो इस बारे में काफ़ी सारी उनकी डिटेल्ड कंपैरेटिव एनालिसिस भी करता है कि कौन सा डिस्ट्रीब्यूटेड है और कौन सा डिस्ट्रीब्यूटेड नहीं है। मैं यहाँ पे आपको उसकी लिस्ट क्विकली शो करने की यहाँ पे अगर आप देखें कि ये जो टेबल नंबर 1, अगर आप मेरी उसको स्क्रीन को रीशेयर कर लें तो वहाँ पे आपको नजर आएगा कि जो डिस्ट्रीब्यूटेड हैं, डिस्ट्रीब्यूटेड एंड हायरार्किकल या डिस्ट्रीब्यूटेड एंड फ्लैट, उनमें काफ़ी सारे प्लेटफॉर्म्स अवेलेबल हैं, स्टार्टिंग फ्रॉम हाइपरफ्लो टू कैंडू, लूम, ओनेक्स, ओनोस। ये सारे डिस्ट्रीब्यूटेड इन नेचर हैं, मगर ये वाली जो डिस्ट्रीब्यूटेड नेचर है ये थोड़ी डिफरेंट है। व्हाट वी कॉल डिस्ट्रीब्यूटेड नेटवर्किंग वाला जो एस्पेक्ट है या डिस्ट्रीब्यूटेड प्लेटफॉर्म जिन्हें हम कहते हैं। कंट्रोलर अगर डिस्ट्रीब्यूटेड है तो इट रिक्वायर्स इंटर कंट्रोलर कम्युनिकेशन। कुछ कंट्रोलर्स प्रोवाइड बाय डिफॉल्ट, उनकी अपनी एपीआईज हैं, कुछ की ओपन सोर्स एपीआईज हैं, कुछ बीजीपी को यूज कर लेते हैं, हम इन्हें कहते हैं ईस्ट एंड वेस्ट बाउंड इंटरफेसेस। सो सम ऑफ देम आर totally distributed and very good at distributed like ODL. So yes, there are solutions which are distributed in nature. You can have multiple controllers communicating with each other, sometimes with other BGP routers, but that is possible.
Thank you. I guess I'll let you know more questions if there are any. They will write me. So thank you very much for such a nice talk again. And I hope we will contact you again for some more details about blockchain. It was
and anytime. Thank you from to all the students and faculty and staff and for arranging this talk. Anytime you want to discuss or go into details of any of these 3 titles or general networking or any such thing, we can have a seminar once again. So from my side, thank you all for coming and listening. I really appreciate the effort all the staff does and all the faculty does in arranging all these things. It becomes difficult remotely karna, but I think